demonstration of all this vector algebra that is done with Excel. Okay, so that is one, just simply vector addition. Okay, certainly the component representation of vectors is crucial. What we started talking about last time. So as you can see right at the top is how the vectors are being edited is really very simple. You can also appreciate the certain advantage of the column representation of vectors because they're so nicely aligned. You both go from left to right as we always do, and at the same time the components are aligned. So you just add whatever those numbers are, you add them together, you have your answer. And then in comparison to what we had over here, so also fine. You can add component-wise vectors one by one and go vertically. That's just as good. But ultimately, we'll see that this is advantageous. And now the results are also visualized with every vector being just a segment with an arrow at the end, starting. I picked specifically point O over there, so they start at point the origin. But at the same time, you can certainly do it with any other origin, as I'll just show shortly. Okay, so and you can see how you add the vectors, and this is like a two approaches through head to toe, head to tail, or a parallelogram at the end. Ultimately, what is really important here is, okay, well, we'll get to the properties of vector algebra that we're going to talk about. But before we do that, let's make sure that we know also that we have subtraction available of vectors, right? So as you can see, the subtraction certainly is defined in the same way as with numbers. So what is that? You have A and B. You're looking for C. Looking for, so this is A, this is B. Yes, A and B. Okay, so we're looking for C, which is what? We don't know anything about addition, subtraction yet. So we're expressing C in terms of addition. So we're looking for C, which is B plus C is equal to A. Okay, B plus C, or B plus C is equal to A. That's what we're looking for, and that's exactly how it is built. Okay, you can see it on the right. That vector is built over there as connecting the two endpoints, the endpoint from the endpoint of B to the endpoint of A, and that creates a new vector which is still located in the wrong place. Never forget that. You have to shift it back to the origin, so that the result of subtraction of two vectors starting at the origin or any other point would be still, once again, starting at the origin. So this is the end result is here, not that, not even this. So we drop out that vector. This is the difference, as you can see. So you can still see what's happening there. So once again, subtraction is done row by row like this. Okay, so addition, subtraction, and now the properties, starting with the commutativity property of addition. So A adding to B, we know that you take the B and attach it to the end of A. That's over there. Okay, A followed by B, copied, and then C is going from the beginning to the end. Okay. However, if we add B to A, it is the opposite. You start with B, attach A, and then copy of A, and then go a straight line. So certainly these pictures hopefully are convincing that indeed these two triangles produce a parallelogram. Certainly to provide a complete argument, you have to look into Euclidean geometry a little bit. But well, actually, if you think about it, these two triangles, what's the relation between them?
Similar?
Not just similar, they are identical, right? Because the sides are the same, right? A and B, same length, and the angle between them is also the same. Okay, there you go. So you have two adjacent sides, and the angle between them determines the triangle. So these triangles two are identical, which means that at the very least the diagonal is the same, and then we just pull them together. Okay, so that is our commutativity property. associativity property is this. So a little bit more complicated. As you can see, so we have three vectors, and we adding them. If you read the first one, it is a plus b first. So just the way we did it here. A plus b, red, green, and then c is the blue one. Okay, and then to that we add c. Okay, so the purple one. Okay, and the end result of the last addition is vector f, which is yellow. Okay. And that's one way to do it. Another way to do it is you add these two first, B and C, green and purple, and that gives me blue, dark blue, which is I call it E. And then to E you add A, and then these two are supposed to be the same. So once again, you can certainly question. You probably need. Euclidean geometry to prove that this is the case, or as we have, it's all about numbers after all. I mean, once you realize that everything is simply done component-wise, then the properties are just entirely obvious because there, if you add, you just take the associative property of numbers and just apply it in every according to every row. Okay, and the result is the same. It's especially simple with commutativity. You just flip to the order of operations. And this is the one from last time. The distributive property. Okay, so here we have what we have. I picked the multiplication, scalar multiplication combined with vector addition. So we have two vectors, and then we have to add and then multiply by 2, add, multiply by 2, or multiply by 2 each of them, and then add. Okay. So once again, you can make an argument that these two are overlapping. They will produce the same result. Okay. So just extra features here. You could just for fun, what happens if I could rotate these. So I'm rotating, what am I rotating? I'm rotating A. So as you can see, A is rotating, at the same time nothing, the result certainly remains the same. I could rotate B as well, and A could rotate, and as you can see, that's what the Excel is capable of. Everything is shifting together, okay, and resizing. So that's what's behind those numbers. That's straightforward to do if you do it with numbers, but then geometry is what really what we care about. Okay, so forces, velocities, that's how they behave. You could do the same with associativity. Once again, rotations are all possible. So when I'm rotating B. Okay, B is rotated, A is rotated as well, and as you can see, everything is. They could pass through each other. That should be no trouble, as you can see. It doesn't make any difference. Negative, positive, it's all good. So now I'm rotating C. Okay, well, it doesn't go beyond that. Okay, so one more property. It is not a property technically, but this is, I want to just illustrate what happens when we ship the not the origin, but rather the endpoint. So we do all the algebra, these two operations, vector addition and naturally scalar multiplication. The vector that is you start with, the initial point should be the same as at the end. Okay, so that's an example. I have three vectors, A, B, C, and then I add them together. The purple one is the sum, and it starts at the origin again. But I could change the point elsewhere. I put say 1 here. Okay, so as you can see, the picture remains exactly the same, just shifted. All the algebra is exactly, say -1. All the algebra is exactly the same. Okay, so we just keep shifting. Okay, so that's why when we do algebra vectors, we just could assume that they all start at the origin, and then whenever if there is a point, we could actually shift our attention to another point, and the algebra will be exactly the same. So the picture is roughly what I'm talking about here is like this. Like this. So every point has a collection of vectors starting at that point, infinitely many, of infinitely many lengths. Okay, so that's every point has this, and so it's not just the origin. Every point has a whole bunch of vectors starting at that point, and then you do algebra with this. So algebra with these. So if you say, well, let all vectors start at the origin, that's fine. That at least you won't make a mistake. Okay. So let me finish this topic. So I want to put the column notation next to the row notation. So this is the row notation for vectors, and you put them one under the other if you want to do component-wise, so that they align. But similarly, you can do it with the column notation, which is in fact even better. You just go horizontally. X plus U, Y plus V, Z plus W. Okay. So they're even though they're interchangeable, but really it is they are not entirely equal. So the latter notation is ultimately the right one. As we shall see. Okay. So once again, component-wise, multiply, and you have a new column. So once again, these are vectors. If you can have 1, 2, 3, or n entries, components in the column. Column vector, row vector, same thing. Okay, so addition, scale, multiplication, all the properties, I didn't list all of them, but it's like 8 properties or so of, I just gave you commutativity, distributive property, associativity. Scale multiplication has it's kind of hard to visualize, it's stretching vectors, but it's more or less predictable what we're supposed to say. But all of these properties, I want to make that point again, allows us to do algebra with vectors, just like we do algebra with numbers, as long as you don't do something that is not allowed to begin with. What I mean is this. All manipulations, vector manipulations, are allowed with vectors, provided one thing is that the expression itself every time should make sense. Which simply means that the only operations that we have defined we are allowed to use. So, addition, scale, multiplication, okay. Addition, scale, multiplication, okay. And then what is not okay? Multiplication of vectors. At this point, we certainly do not multiply vectors. Okay, so that's no. Division, definitely not. I don't know, logarithm, exponential function of vectors, all of that out of the question. And the worst case is, of course, as always with mixing units, vectors plus numbers. That's also bad. Okay, so this is all a no. But if you have an expression and all operations are aligned correctly, so you're adding vector to vector, number to number, you multiply number by vector or number by number, and then you start treating what you see as if it is just an expression of numbers, then you will be okay with all of those simplifications because you have those 8 properties of algebraic properties of vector algebra. Okay. Okay, so let's see. So that's what we just been talking about. Multiplication by 0 of a vector gives you zero vector. Adding zero vector to any vector gives you an A, and then there's all of them. Say there is a special negative vector. A plus negative A is equal to plus negative A is equal to zero vector, and so it's all of these properties that they're very obvious as long as you're using numbers. They are just as well applicable if we talk about vectors. Okay, we're switching to coordinates to components, so the word for the same numbers. This is exactly the same numbers. So look at the example on the right. If we start at the origin and the end point is at P, then the coordinates of P, the point, are the components of the vector OP. Okay, so that's what you see on the right. So it seems to be exactly the same. But that only works out if we only just decide once and for all, or at least for a while, only concentrate on vectors starting at origin. Okay, then there is no conflict, even though it is still a good idea, like good grammar. It's a good idea to remember that we do certain things with vectors, and we don't do certain things with points. Okay, so let's review that, and let's review that. So points. So they have coordinates to begin with. Okay, then what we can do with them, we can do their distances. So there are distances between them. Okay, there is no algebra. We don't add points. Okay, with vectors, even though maybe given by the same number of numbers, so they have 4 components, which we're going to discuss, and then there are angles also to be discussed between them. Well, there there are 2 points. There could be no angle between them, but between vectors, certainly that makes sense. And then we do algebra. The only thing to overlap is actually we could talk about what is if we want to measure vectors. We want to measure vectors. After all, the informal explanation of vector is directed segment, and its segment has a length. So that portion is uncomplicated. We have a vector, then the length of vector, say PQ, is the distance from P to Q. Okay, so the angles are still to be discussed, but we certainly can easily take care of the lengths. Just if you have the initial points available, then this is vector PQ, and we can speak of the magnitude. Also, another term is the magnitude, the length, or the other term is the magnitude. And it's simply computed as the distance. Well, once that is established, then the formula is very simple. So it's a length formula. So if, say, vector A is given by its components, say A1, A2, AN. Okay, so, well, in dimension 3, that certainly is transparent more or less. We are talking about this vector A, capital, and this is the endpoint P, and what we're doing is we're measuring the distance between the origin and P. So all we have to do is just to apply the distance formula. This is the notation for the magnitude or the length of a vector. Vertical lines, which resembles the absolute value, not by coincidence, it is because in dimension 1, the magnitude is the the absolute value. Okay, but other than that, we just all we have to do is just to take the apply the distance formula. Distance formula applied not to vector, but initially to apply to those 2 points OP, and fortunately, as we just established, is in that particular case, the coordinates of P are the components of OP. Okay, let me write it down. Coordinates of P are the components of OP. Okay, and then if we plug them into the formula, them being the components, same as coordinates, we have our formula. So it's a1 squared plus a2 squared, an squared. Okay. So the formula is useful whenever you have to compute something about every time you have to compute a specific vector, you want to compute its length. But it is just like with the distance formula, just a way to compute it. And remember, there are many ways to define it in the first place, and their formula varies from dimension to dimension. So that's why it is. Let me write it this way: the magnitude is equal to the distance from O to P. Well, let me put it here like this. So OP. The magnitude of this vector is the distance from the origin to the endpoints. Okay, so remember this notation is a compact notation, a very convenient notation that allows you to treat all the distances in all dimensions in all situations in the same size simultaneously and similarly. You just say whatever the setup that we started with, this is how we measure distances, then well, let's just use it as it is. Okay, so with that, once the distance has been defined, we can measure distances using the properties of distance. And similarly, remember the properties was remember those three properties of distances. Distance is never negative. It is only equal to 0 to them when 2 points are equal. That's number one. Number two is distance from P to Q, same as from Q to P. And thirdly is the triangle equality. Okay, so these are the only three properties that is quite sufficient to solve a variety of problems in any dimension that you encounter. Similarly, now we take this idea and apply it to vectors, and then that is the connection right here. And then once again, the idea is not really relying on properties as much, just understanding that it's often not that important what is the formula, what is the specific formula for computing the magnitude is, but rather sometimes just properties just like these are even more convenient. So let me just give you a couple that they're uncomplicated. So for example, what does it do to, well, let's start with the triangle inequality, like this, PQR, right, R, and this distance plus that distance is larger than or equal to the distance from P to R. Okay, now if we restate it in terms of for vectors, so these are distances. Now let me write it out. So distance PQ plus from P to Q with a comma, distance from Q to R is larger than or equal to distance from P to R. Okay, so now using this formula, right, the transitional formula for transitioning from distances to magnitudes. So let's take the triangle inequality for magnitudes.
Just magnitude PQ?
Yeah. Magnitude PQ, yes, plus magnitude QR is larger than or equal to magnitude of PR. Okay? But we can do more than that. we can do more than that. If you look at the picture on the right, there is actually a relation between unlike those distances, P, Q, and R, three points unrelated to each other. If I take these two vectors, I rename these as A, B, and C, there is an algebraic relation between them. Okay, so let's utilize that. So I start A magnitude plus B magnitude larger than or equal to what?
Magnitude of C.
Yes, but look at the picture.
C, man.
I substitute what for C?
It should be PR.
PR, thank you. Yeah. Okay. So, so this is C. How does it relate to A and B?
E minus A.
What?
E minus A.
No, it's plus. A plus B.
Oh.
Okay, so that's just another triangle inequality. So this is, the original one is here, and we have a new version which is for vectors. It's exactly the same thing, right? Look at the two pictures, they're the same. Just, do I have arrows there or not? Do I name points or name sides? Remember that? You do it casually, routinely in geometry, you name sides. This time we're not naming sides, but rather vectors between points. But as you can see, we use our algebraic operation on vectors really very, very nicely. So once again, two still recognizable. The relation between the two is still recognizable. So that is the relation between the magnitude and vector addition. That's the main one. Really nothing more much you can do. But there is more, and that is the scale multiplication. So what's the relation between the algebra, the scale multiplication, and the magnitude? Well, if I stretch by vector C, by a number C, take my vector, stretch it by C, so this is A and this is CA. Okay, what happens to the magnitude?
Vector of C.
Yes, almost. What if C is negative?
We take the absolute value.
We take the absolute value. Yeah, then it works out just fine. So, because in case we multiply by a negative number, you remember the magnitude has got to be always non-negative, as we define in that purple square box at the top. The magnitude cannot be less than or equal to 0. The magnitude, or what else? This is the property, magnitude cannot be less than 0. The magnitude is equal to 0 only when the vector is what? A is equal to 0, if and only if. What? The vector is 0. Once again, distances, it's the relation between distances and the vectors. The point and the distances and magnitudes. Yeah. And secondly, that you can guess, say, the magnitude of A is equal to the magnitude of negative A. Okay, so once again, that's the second property over here. Going left, right, right, left, it doesn't matter the magnitude. The distance is the same and the magnitude of the vector is the same. Okay, so there are a bunch of properties that come either directly from properties of distances, or we may introduce also the algebraic operation, these two, to the picture. But these are make our computations quicker when necessary. And once again, you should appreciate that this is entirely applicable to dimension. And I intentionally scroll down so that, as you can see, there is no distance formula here involved anywhere, and yet we can do a lot of algebra with the vectors and magnitudes without invoking that formula or even thinking about the dimension, because everything is pretty much the same. Okay, so now, so that's something to be used in the future a lot. Now, what else we need to discuss is a little bit about, more about components, and actually the reason why, or why we use that word in the first place. Well, components come from decompositions of vectors. The way we have started is that we in fact decomposed our vector. Say this is P and its coordinates are say 2, 1. Okay, my vector A here is OP and it is equal to the vector with components 2 and 1. What's the meaning of 2 and 1? What can we, how we can receive 2 and 1 without referring to point P, but rather referring to vectors otherwise present? And the answer is this: if I decompose my vector correctly, I could. The point being is considering the two directions separately. Okay, so this is what I mean: 2, 0 plus 0, 1. That's the initial decomposition of the vector in the plane into two separate directions with respect to x and separately with respect to y. And then furthermore, this is, so I use the, I'm moving backwards with the vector addition. So instead of adding vectors, I take a vector and decompose it into a sum of two vectors. But I could take it beyond that. I could factor 2 out. 2, 1, 0 plus 1 times 0, 1. Okay, so it looks strange maybe at first, but really these two numbers are our components. So these are components. So these are the meaning of the components. So they are how many 1 zeros. That's the first one, and how many 0 1s. Okay, so if we have two, as they call the basis vectors. This is 1, 0, and this is 0, 1. So these are two basic vectors, are they of the unit length, and they follow either one of the other axes. Okay, and then we can express, as you see on the right, the new vector, every vector, in terms of these components. So once again, how many of the first one? They have actually special names, I, j, and k in dimension 3, and how many of each kind we have. Okay, so well, let me just do one more in dimension 3. So if I have a vector A with components, say 2, 3, negative 1, then I decompose it into well, let me just introduce those vectors, I, j, and k. So instead of thinking in terms of axes, we could concentrate on those vectors. I along the x-axis, g along the y-axis, and k along the z-axis. Okay, so once again, it is 1 and 1 and 1. Okay, so these are basic vectors. It turns out that we can express every vector in terms of those. Okay, so once again, and how very elementary. If we have a component representation, we have already like this is 2i plus 3j plus negative 1k. That is the decomposition, the component decomposition. So you can see how every number reappears in the decomposition. In that order. So on right is one vector written in terms of its components. On left, on the right it is the sum. It is the sum of three special vectors with addition, a vector addition, as well as scale multiplication. Okay, so that is certainly not something new. It is It is very similar to what we have done as far as the motion is concerned, and you can split the forces or velocities along different directions. The point of introducing this, not just components like this, but rather basic vectors, basis vectors, is so that they could be changed. Okay, so they can be changed with the for a new Cartesian system. So just as with points, changing Cartesian system will change their coordinates. Similarly, if we change the Cartesian system, it also changes the components of the vectors, and then this is what happens. You can imagine that I, j, and k might be different. In addition to what we just talked about, the origin might move. So origin might move. Say, you can put the origin of the center of the universe at the Earth, or maybe at the Sun. It doesn't really matter. We can keep switching back and forth as necessary. It is a matter of convenience. Okay, so certainly the formulas of motion of the planets would be easy to write if you choose the Sun to be the center, to be the origin. Okay, and that's to begin with the origin, but then now back to the vectors. Some directions are more advantageous depending on the circumstances. For example, well, here's an example. What if we have some kind of inclined motion? Okay, so this is an object that is sliding or rolling down the slope, and then we know the gravity is still pulling it down, but it doesn't matter that it's pulling it down because some part of the of that force will be lost because of it's canceled out by the resistance of the slope. So like this. Okay, so this is the decomposition of the forces. So the green one is the actual gravity, right? But you can certainly work out in this fashion. But if you were considering many objects and some complexity of the problem to be solved, you could replace the two-dimensional problem with one-dimensional because the motion is only one-dimensional. You can do it if you are able to choose the coordinate system appropriately to your advantage, which will make things simpler. And you realize that, well, it's already visible. What should be, you should probably choose like I this way and j that way. Okay, so that there would be no motion with respect to j, only with respect to I. And then if you may have started this way, say I and j, that is one thing, and that would be a two-dimensional motion along some straight line. But if you choose your axes along one of the axes along the slope, that problem will be much easier to handle. Imagine that, or maybe imagine that the slope is curved. So that would be really interesting to think about. Then you realize that following that idea, you have to actually you have to change. There will be different basis vectors depending on the location. Okay, so that's the a different degree of complexity. You can think about if you were talking about, you would put the center of the universe at the origin at the Sun, but then if we are studying what's happening on the Earth, then we actually we'd rather have our system of coordinates connected to the Earth rather than to the Sun, if that Sun does not contribute anything. So it will be keep changing the direction. So you don't want to compute those directions every time as the Earth is rotating. So once again, another choice of the coordinate system. If you have a plane, once again, you know how they do it. You actually associate with the plane another three vectors, and those three vectors that keep moving. They call it a frame because you do this, you do that, and then there's a change of axes, and therefore of the basis vectors all the time. And but that's the way to do it. You don't want to. Actually, just a matter of simplicity. So we're not going to go into that, but what I want to do is this examples that I showed you of how different axes or different Cartesian system where different directions are chosen depending on the nature of your problem. You could also, you could actually do it the same even if you have abstract spaces. So this is a reality, and in reality everything is happening, and it might dictate the choice of the coordinate system for us. But in abstract spaces, as we talked about, what was the wheat against sugar, and that the two directions, x and y, and it seems that there is no point of changing, or choosing a different coordinate system. But actually, there might be, depending on how deep you want to go into that. So this is the example I made up. So if instead of commodities, we look at the stocks, okay? And suppose we're talking about, let's say we have a GM stock here, how much you want to have, and then let's say ExxonMobil is another one. So certainly if you are, this is the point, what is presented, it presents a simple portfolio with two stocks, and it shows how much and in what proportions you have them. Okay, so that's the only thing. These might be measured in totally different units, and as we talked about, it's not easy to substitute to resize the dimensions of the vector horizontally or vertically, and that would ruin everything, and distances would be hard to measure. But not necessarily algebra. Algebra is more stable that way. So here's what I could try. What if this? Well, let's say when we take some famous investor, say, what's his name, Warren Buffett, and suppose this is his proportion of GM and ExxonMobil that he has. Okay, then we could actually choose our axis like this along with that person, so that you know that the proportion of these two companies that he holds, and he thinks for some reason that it is the best way to do it. So then you can compare your own portfolio to Warren Buffett's portfolio, and then what do? You look at this like this. You find that you decompose your portfolio, this one, into two. Okay, 1 and 2. So let's say the red one is the one that goes parallel to this line. It shows you how close your choice is to Warren Buffett's, and the other one shows you how different it is. Okay, so this is the difference between his choice and yours. Okay, so that might be in some way revealing about what you should do. Maybe you should minimize it, maybe you should not, depending on the circumstances. But once again, you could, if you want to go into stuff like that, you will decompose the whole 10,000-dimensional space of stocks into, and then you possibly could choose coordinates that are different from the natural one along each of the axes. Same with commodities or anything you can come up with. That's what the scientists do. So they have this data, and then they may try to look for patterns, and that would be one of them. So anyway, the point being that the axes change, the basis vectors change, and we should be able to express each of them separately with respect to our choice of axis. So for example, just as a simple example as it gets, so this is still the what we have started with, and I might have once again maybe 2, 3 my vector. Okay, so vector A, 2, 3. But we know that it is 2I plus 3j. We choose our vector. This is my I and this is my j. Unit vectors along the two axes. But then I decide what if I switch and I choose, for example, the geometry will be the same, the distance will be the same, but I choose, let's keep it simple, and I'll just choose, say, I capital and j capital, like this. Okay, 2 other basis vectors. So f2, this is -1 and this is 2. Okay, so my vector is still the same, so it's still here, like this. Okay, so that's still my vector A. Now I want to represent A in terms of of I capital J capital. Okay, so can you see?
So, 1 negative
1 negative 3. 1 negative 3. So let me show it. So okay, so this is the easiest one, right? If I just go down, I know that I go 2 horizontally, which means that the horizontal component is 2. So if the current horizontal component was 2, it remains 2, and that's why. And that's why it's horizontal core. No, it's a component. Its component with respect to I is 1. Okay, so horizontal component is 2. That is why its component with respect to I is 1. So how many I do I need? I need only 1 I horizontally. Now, as far as J is concerned, as you can see, our vertical component is 3. So how many J's do I need? How many J's do I need? I need 3 only going in the opposite direction. Okay, so this is 3. So how do I get to 3? Taking J steps. And the answer is negative 3. So in that sense, as you can see, we have a totally new representation of our vector with respect to different coordinate systems. Okay, so